Hi students, in this session I will explain you about the topic linear time invariant system. Linear time invariant system. Simply we'll call it as LTA system. Okay. What is an LTA system? Or when a system may be called as an LTA system. Simple. A system is said to be an LTA system, that is, if a system is said to be linear time invariant system, it has to satisfy both linearity property and time invariant property. It has to satisfy both linearity property and time invariant property. Then we can call that system as a linear time invariant system, or simply a system which is both linear and time invariant is called as an linear time invariant system. That is, if a system is linear as well as time invariant, then I can say that system as a linear time invariant system. Okay. So, simple. A system which is linear as well as time invariant is called as a linear time invariant system. And you all know what is linear. What is linear? So here linear means it has to satisfy both superposition and homogeneity principles. It has to satisfy. That means the system has to satisfy both superposition and homogeneity principles. Superposition and homogeneity principles. That means the superposition and homogeneity principles are valid. In addition to that, it has to satisfy time invariant. For time invariant, the input and output characteristics do not change with time. So, in time invariant, the input and output characteristics do not change with the time. They do not change with time. That means, if there is a delay in the input, by capital T seconds, then the output will also be delayed by a same capital T seconds, then that is a time invariant. That is, the input and output characteristics do not change with time. So, first, for an LTA system, it has to satisfy linearity and time invariant. Okay. Linearity means the principles of superposition and homogeneity should be valid. Time invariant means there should be no change with time of input and output characteristics. That is, the input and output characteristics do not change with time. Input and output characteristics do not change with time. Okay. So, if I want to say a system as a linear time invariant system, it has to satisfy superposition and homogeneity principles. Along with this, the input and output characteristics do not change with time. If it satisfies all this, then I can say that system is a linear time invariant system. So, here a superposition and a homogeneity, you all know, I already explained you while I am explaining the concept of linearity. Now, I will explain the input and output characteristics do not change with time. Okay. Here, if there is a delay in the input, if there is a delay at the input by capital T seconds, that is, input is delayed by some amount. If the output is also delayed by the same amount, that is, the output is delayed by the same capital T seconds, then we can say that the input output characteristics do not change with time. Input output characteristics do not change with time. Clear? See, here, the output due to the delayed input. The output due to the delayed input. See, here the input is delayed by capital T seconds. Let's consider the input is delayed by capital T seconds. So, the delayed input is represented with x of small t minus capital T. We all know this. Because if there is an advance, then you have to represent with x of small t plus capital T. If there is a delay, we have to represent with x of small t minus capital T. Now, this is the delayed input. This is the delayed input. So, see, the delayed input is x of small t minus capital T. If this is given to a system and the system is producing an output and the system is producing an output, if the output of the system is equal to delayed output of the system is nothing but the delayed output, that is the output is also delayed by same capital T seconds. The output is also delayed by same capital T seconds, that is y of t minus capital T. Then I can say this system as a linear time invariant system. Then I can say this system as linear time invariant system. Simple. Okay. See, the output due to the delayed input. Here the delayed input is this one, x of t minus capital T. Delayed input. That is, the input is delayed by capital T seconds, and that is given to a system as input, and the system is producing an output. If that output is equal to the delayed output, that is, if the output is delayed by the same capital T seconds, that is, that can be represented as delayed output, y of t minus capital T. Input is delayed by capital T seconds, x of t minus capital T. Output is delayed by t seconds, that is y of t minus capital T. If it produces a delayed output, that is output is delayed by the same capital T seconds, then I can say this system as an linear time invariant system. Okay. Simply, the output due to delayed input, the output due to delayed input. Here the delayed input is this one, and I am representing that as y of small t comma capital T. Here y of small t comma capital T is the output due to delayed input. This is the output due to delayed input. That is, I had delayed the input by capital T seconds and I had given to the system and it is producing an output. I am representing that output as y of small t comma capital T. If that output is equal to the delayed output, this output is equal to the, if the output is equal to the delayed output is y of t minus capital T, then I can say the system is linear time invariant system. Simple. So here I am considering this y of small t comma capital T is the output due to the delayed input. That is, the input is delayed by capital T seconds and this is given as input a system and it is producing some output. I am taking that output as y of small t comma capital T. Y of small t comma. If that output is equal to the, delayed output, the output is equal to the delayed output, that is y of t minus capital T, then I can say this system is a linear time invariant system. So the condition is this one. This is a very, very important one. The condition. Here, y of small t comma capital T is the output due to the delayed input. And y of small t minus capital T is delayed output. If both are equal, then I can say there is an LTI system. Okay. That is, input is delayed by t units. The corresponding output will also be delayed by capital T units. That is, if there is a delay of capital T seconds at the input side, then the output will also be delayed by the same capital T seconds. That is, the input output characteristics do not change with time. Whatever the delay is at the input, the same delay will be at the output. The input output characteristics do not change with time. Those type of systems are called as linear time invariant systems. Simple. Here we have to consider input is delayed by t units. Then the corresponding output will also be delayed by capital T units. Clear? So this is a simple explanation about LTI systems. And the last point, for an LTI system, all the coefficients of the differential equation describing the system should be of constants. Simple. If I am describing the system with a differential equation, okay. So if I am if I am describing this system, our LTI system, with a differential equation, then the coefficients of that differential equation must and should be constants. Must and should be constant. So for an LTI system, all the coefficients of the differential equation which describes the given system must and should be the constants. They are all constant. There is coefficients. We have to write dy by dx square, dy by dx. The coefficient of that one, the coefficient of that differential equation must and should be a constant. Must and should be a constant. Okay, that means the differential equations are multiplied with the constant coefficients. Then I can say this as a linear time invariant system. Or if it is a linear time invariant system, then the coefficients of the differential equation which describe the system are constants. Very, very important point, this one. So on seeing the equation, if there is a differential equation, on seeing that equation, if all the coefficients of the differential equation are constants, then I can simply say that is an LTI system. Or simply for an LTI system, the coefficients of all the differential equations which describe the system are constants. Okay, this is completely about linear time invariant system. Now we will move on to the linear time variant system. Now we move on to the topic linear time variant system. Okay, the linear time variant system is simply represented with LTV. L for linear, T for time, and V for variant. Linear time variant system, that is simply LTV system. So when I say a system is a linear time variant system, so if I want to say a system as a linear time variant system, it has to satisfy the linearity as well as time variant, but not time invariant. Here it is a time variant. That is, time variant means the input output characteristics change with respect to time, and linearity means linear means it has to satisfy both the principles of superposition and homogeneity. So whenever a system is a linear but time variant is called an linear time variant system, or simply LTV system. Okay, a system which is linear but time variant is called a linear time variant system, or simply LTV system. Okay, see here, this system is linear but time variant, that is, it is not time invariant. Not time invariant means time variant. That is, the input output characteristics will change with respect to time. If there is a delay of t seconds at the input, then at the output the delay is not t seconds, other than a t, anything it may be. Okay, so the delay at the input is not same as delay at the output. If the input is delayed by t seconds, then output will not be delayed by t seconds. It is a value other than t. Then I can say that system is a time variant. That is, the input output characteristics change with the time. Okay, now come on to the linear. So we all know the linearity. So when we say system is linear, if it satisfies the principles of superposition and homogeneity, then I can say that system as a linear system. Okay, see, if I want to say a system as a linear time variant system, first it has to satisfy the principles of superposition. It has to satisfy the principles of superposition and homogeneity. That is, superposition and homogeneity principles are valid. They satisfy both this. But see, the input output characteristics change with time. But the input output characteristics changes with time. Then I can say that system as a linear time variant system, or simply LTV system. Okay. So if you want to say system as a linear time variant system, it has satisfied the principles of superposition and homogeneity. Superposition and homogeneity principles are valid, but the input output characteristics but the input output characteristics change with time. See, how can we represent it in the form of an equation? Means simply let us consider the output due to delayed input. The output due to delayed input. Let us consider there is a system. There is a system. For this system, I am giving the input as delayed input. X of t is input and the delayed by capital T units. Then I can write that as x of small t minus capital T. Okay. So this is the input. This is the input for the system. That is the delayed input x of small t minus capital T. Now the system will generate an output. Now the system will generate an output. That is output due to delayed input x of t minus capital T, and I am taking that output as y of small t comma capital T. Y of small t comma capital T. Okay. If that output is not equal to the delayed output, if this output y of small t comma capital T is not equal to delayed output is y of small t minus capital T. If it is not equal to the delayed output, then I can say the system as linear time variant system, or simply LTV system. LTV system. That is, you can represent the equation like this: y of small t comma capital T is not equal to y of small t minus capital T. So this y of small t comma capital T is nothing but the output due to the delayed input. This is output due to delayed input, and this is the delayed output. If those both are not equal, then I can say that is an LTV system. Okay. If the output due to the delayed input is not equal to the delayed output, then I can say that system is a LTV system or linear time variant system. Simply I can represent that equation as y of t comma small t comma capital T is not equal to y of small t minus capital T. Okay. Now see, here I said input is delayed by t units. Here the input is delayed by t units. Hence I write it as x of small t minus capital, delayed by t units. The corresponding outputs will not be delayed by exactly t units. That is, the corresponding output will not be delayed by exactly t units. Hence I write it as not equal to. That means the output of the system is not equal to the delayed output. Why? Because the output will not be delayed by exactly capital T units, because the input is delayed by capital T units. Here the output will not be delayed by capital T units. That is, it has to be delayed by another value. Okay. So the output for a given delayed input must and should not be equal to, it's not equal to delayed output, that is not equal to y of t minus capital T. Okay. Now consider for an LTV system, at least, this is an important one. For a LTV system, at least one of the coefficients of the differential equation describing the system vary with time. At least one of the coefficients of the differential equation describing the system vary with time. Now, if the system is describing by a differential equation, now at least one of the coefficients of that differential equation varies with time, then I can say that is a linear time variant, because the name itself is time variant. That is, one of the coefficients of the at least one of the, that is one or more, you can say one or more. Hence I said at least one of the coefficients of this differential equation describing the system vary with time. If those coefficients vary with time, that is, they are not constants, so the coefficient must be like 2t, t square. But the coefficients has to vary with time, they should not be constants. Then that will give a linear time variant system. That is, if the coefficients of the differential equation describing the system vary with time, then that will be a linear time variant system. Or simply, for a linear time variant system, at least one of the coefficients of the differential equation describing the system vary with time. Okay, so this is regarding linear time variant systems. Okay, so previously I explained you about linear time invariant system, LTI system. Here I am explained you a LTV system, that is linear time variant system. Now see the important points regarding this LTI and LTV systems are, let's say, continuous time systems. Continuous time, see, every time I use small t, so this x of small t, y of small t means these are continuous time systems. Okay, these continuous time systems are described by differential equations. Generally, in general, these continuous time systems, that is, if x of t is given as an input to the system and it is producing an output y of t, then that continuous time system is described by differential equations. Continuous time systems are described by differential equations, and they can be analyzed. Those can be analyzed using either Fourier transform or Laplace transform, and they can be analyzed by using either Fourier transform or Laplace transform. So the continuous time systems are generally described by differential equations, and they can be analyzed. We want to analyze those systems, that can be done either by using a Fourier transforms or Laplace transforms. So first I will describe the system with the differential equations, and I will analyze by using either Fourier transform or Laplace transform. Here in this Fourier transform and Laplace transform, analysis using Laplace transform is easy and more convenient when compared to Fourier transform. If I compare Laplace transform and Fourier transform, analysis of this using Laplace transform, is more easy or more convenient, when compared to Fourier transform. Why? Because simply this Laplace transform is more powerful. In the sense that for many functions a Fourier transform does not exist, but Laplace transform exists. Here, for most of the functions for which the Fourier transform does not exist, Laplace transform will exist. Simple. If I want to analyze, okay, for the analysis I will use Laplace transform and Fourier transform. In these two, Laplace transform is easy and more convenient and compared to Fourier transform. Why? Because simply this Laplace transform is a powerful technique, okay, is more powerful. This Laplace transform is more powerful when compared to Fourier transform. Why? Because for most of the functions or for many functions, Fourier transform does not exist. But Laplace transform exists. For many functions or for most of the functions, Fourier transform does not exist, but Laplace transform exists. So if there is an existence of Laplace transform, then analysis is taken. But if the Fourier transform does not exist, how will we analyze? So for analysis, that Fourier transform or Laplace transform has to exist. Here, for many functions, the Fourier transform does not exist, but Laplace transform exists. So Laplace transform is more powerful and it is easy and more convenient when compared with the Fourier transform. Okay, or simply Fourier transform is obtained from Laplace transform. We can obtain the Fourier transform from Laplace transform just by replacing S in the Laplace transform with j omega. If I replace S in the Laplace transform, if there is a Laplace transform equation, if I replace S and put j omega, then that will give the Fourier transform. That is, I can obtain the Fourier transform from Laplace transform just by replacing S with j omega. Okay, so for that we will mostly prefer Laplace transform. If I got the Laplace transform, automatically from the Laplace transform I will get the Fourier transform by replacing S by j omega. So in most of the cases we prefer Laplace transform. Or simply when frequency response is required, so I need a frequency response spectrum, that is frequency domain. Whenever I need the frequency response, the transfer function, we all know the transfer function, h of omega, frequency response is in frequency domain, so we have to go for the frequency spectrum. That is, the transfer function h of omega is obtained using Fourier transform. So the transfer function h of omega is obtained using Fourier transform in simple cases. In simple problems, in simple equations, we will go for finding the transfer function h of omega from Fourier transform. And for this frequency response, I will get the transfer function from h of s, okay, in complex cases. H of s from h of s, that is h of s we can find out by using Laplace transform. That is, for complex cases I will go for the Laplace transform. From that I will get the h of s transfer function. So whenever frequency response is required, I go for the transfer function h of omega, which can be obtained from Fourier transform in simple cases, and I go for h of s, which is obtained from Laplace transform in complex cases. So in complex cases I will go for the transfer function h of s, which is obtained by using Laplace transform. Is obtained by using Laplace transform. In complex cases. Simple. Okay. So this is about the how we analyze. So this first I will represent this continuous time system using differential equations, and we can analyze either using Laplace transform or Fourier transform. In those two, mostly we will prefer Laplace transform, and Laplace transform are used in complex cases. So whenever the frequency response is required, I will go for the transfer function h of s from Laplace transform in complex cases, and in simple cases I will go for the transfer function h of omega, which is obtained by using Fourier transform. That is, simple cases I will go for h of omega from Fourier transform. In complex cases I will go for h of s from Laplace transform, and the Laplace transform is easy and more convenient and powerful when compared to the Fourier transform. Simply why? Because for many functions the Fourier transform does not exist, but Laplace transform exists. So this is the topic regarding the linear time variant LTV systems and Laplace transform and continuous transform, that is, and the analysis of these systems, okay, by using Laplace transform and Fourier transform, and which one is more convenient and more powerful and more easy to go for the analysis. Okay, now we move on to the properties of linear time invariant systems. Simply now I will explain you the properties of LTI systems. Now I will explain you the properties of LTI systems. So before going to the properties, first we see the characteristics of an LTI system. The characteristics of an LTI system are completely determined by its impulse response. That is, I already told you the impulse response will play a major role in the analysis of this LTI system. So the characteristics of an LTI system are completely determined by its impulse response. So whenever there is an LTI system, linear time invariant system, if I want to know the characteristics of the system, that will be determined by its impulse response. That is, if I know the impulse response of that system, that LTI system, then I can know the characteristics of that LTI system completely. Okay, so important one. How can you know the characteristics of the LTI system? Just by knowing its impulse response. So the impulse response plays a major role while analysis or finding the characteristics of the system. Okay, so the characteristics of an LTI system are completely determined by its impulse response. So whenever there is a system, simply it is an LTI system, if you know the impulse response, if the impulse response of the system is h of t, then I can completely determine the characteristics of this system by using this impulse response h of t. So we know that the impulse response is represented with h of t. If I know that, I can get the characteristics of that LTI system. The important representation of continuous time LTI system is the important representation. So we can represent the continuous time LT systems in many ways. One of the most important representation, an extremely important representation of continuous time LT system is in terms of its impulse response. Because if I know the impulse response, then I can know the characteristics of that system. So one of the most extremely important representation of that continuous time LTI systems is in terms of its impulse response. So I will represent this continuous time LTI systems in terms of its impulse response. I will represent it in terms of its impulse response. Why? Because if I know the impulse response, if that is in terms of impulse response, by knowing the value of that impulse response, I can find the characteristics of the system. Hence, the most important representation of this LTI systems is in terms of its impulse response. Simply, it takes the form of convolution integral. That means, if I represent the continuous time LTI systems in its impulse response, then it will take the form of convolution integral. There we use the concept of convolutions. There the convolution concepts will be useful. That is, it will take the form of convolution integral. Okay, simple. Now we move on to the properties. Some of the most basic and important properties of continuous time LTI systems. That is, continuous time linear time invariant systems are. I am going for the most basic and important properties of continuous time LTI systems. There are, first one, commutative property. The first one is commutative property, and the next one is distributive property, and the third one is associative property. Commutative property, distributive property, associative property. Okay, these three are the basic and important properties of this continuous time LTI systems. So we will see one by one. I hope you already know this one, but I will explain this commutative property in terms of impulse responses. Okay, that is nothing but the concept of convolution integral. It takes the form of convolution. I said it will take the form of convolution integral. So I will explain this with respect to the convolution. Okay, so first I will start with the commutative property. Okay, so a basic property of convolution in continuous time is commutative property. Basic property of convolution in continuous time. So convolution in continuous time is commutative property. So we all know the commutative property. That is simply like A into B equal to B into A. Okay. So based on this, I will go for the commutative property of convolution in continuous time. So it is continuous time. So I have to go for x of t, y of t, h of t like this, because they are saying continuous time, and we have to go for convolution in continuous time. Convolution. So here I will consider the signal input as x of t, and the impulse response as h of t. I already told you. So the impulse response of the system is represented with h of t, and if I say the system has an input x of t, then x of t convolution h of t will be equal to h of t convolution x of t. Simple. X of t convolution h of t will be equal to h of t convolution x of t. Okay, and you know formula of the convolution. The convolution formula is, for this integral, minus infinity x of tau into h of t minus tau d tau. So this one is nothing but this one. So x of t convolution h of t will be equal to integral minus infinity to infinity x of tau h of t minus tau d tau. In the same way, h of t convolution x of t equal to integral minus infinity h of tau into x of t minus tau d tau. So I have written the formulas of convolution formulas. Okay, so just for this the convolution formula is this one. For this the convolution formula is this one. That is, the four are same. So we can represent as an x of t convolution h of t, that will be equal to h of t convolution x of t. Here x of t is the input to the system, and h of t is the impulse response of the system. So x of t convolution h of t will be equal to h of t convolution x of t. Okay, the same as integral minus infinity x of tau h of t minus tau d tau, that will be equal to integral minus infinity h of tau x of tau t minus tau d tau. Same formulas. See, we all know the output will be given by this x of t convolution h of t. I already explained you. So x of t convolution h of t will give the output. Simply, the output of an LTI system, the output of an LTI system with input x of t and unit impulse response h of t is x of t convolution h of t, and the output of an LTI system with input h of t and impulse response as x of t. Consider input as h of t and impulse response as h of t. Both are same, both are identical. That is, the output of an LTI system with input x of t and unit impulse response h of t is identical to the output of an LTI system with input h of t and impulse response x of t. So for the system, if the input is x of t and the unit impulse response is h of t, then it will produce an output. That output is identical, same as the output of the system with the input as h of t and impulse response as x of t. Impulse response as x of t. So I know the output. If I know the impulse response and the input of the system, how can I get the output? So output is nothing but the convolution of that input with the impulse response. So in the first case, the input is x of t and the impulse response is h of t. So x of t convolution h of t. Okay. The second case, if h of t is the input and x of t is the impulse response, then the output is h of t convolution x of t. But both are equal. That is nothing but commutative property. X of t convolution h of t equal to h of t convolution x of t. So the output of an LTI system with the input x of t and impulse response h of t is identical or same as the output of an LTI system with the input h of t and impulse response x of t, or simply x of t convolution h of t will be equal to h of t convolution x of t. So this is the commutative properties, and these two are the formulas for these two. Hence I written the four as same. So this is regarding the commutative property. Okay, next we go on to the distributive property. We move on to the distributive property. The second one, that is distributive property. Another basic property of convolution is this distributive property. Specifically, the convolution distributes over addition. Here, the convolution distributes over addition. That is, see, x of t, the input signal, x of t convolution of h1 of t plus h2 of t will be equal to x of t convolution h1 of t plus x of t convolution h2 of t. We already know the distributive property. A into b plus c will be equal to a into b plus a into c. In the same way, here it will follow the convolution. The convolution distributes over addition. That is, it follows the x of t convolution h1 of t plus h2 of t will be equal to x of t convolution h1 of t plus x of t convolution h2 of t. See here, x of t is the input signal. X of t is the input signal. Okay. Now, h1 of t is the impulse response of the first system, and h2 of t is the impulse response of the second system. Okay. Now, x of t is given as input to a system whose impulse response is a combination of h1 of t plus h2 of t. Okay, and it is producing an output y of t. It is producing an output y of t. Okay, then that y of t is equal to x of t convolution h1 of t plus x of t convolution h2 of t. Okay, simple. See this one, x of t convolution h1 of t plus h2 of t. That is, I am giving an input of x of t to a system whose impulse response is the summation of h1 of t plus h2 of t. Okay, and it is producing an output y of t. So x1 of t convolution h1 of t plus h2 of t. See this one, and that will be equal to x1 of t convolution h1 of t. So this is the impulse response of system 1 plus x of t convolution of h2 of t. And these are the system 2. System 2. So this individual combination, this individual convolutions, the addition of the individual convolutions is equal to the convolution of addition of their impulses. Convolution of addition of their impulses. Okay, I shown the diagram. See here, I shown this in the diagram. So x of t convolution h1 of t plus h2 of t will be equal to x of t convolution h1 of t plus x of t convolution h2 of t. So this system is producing an output y of t, and this is also producing an output y of t. Here the both y of t's are equal. That is nothing but our distributive property. Simple. Two systems with impulse responses h1 of t and h2 of t are connected in parallel. When two systems having impulse responses as h1 of t and h2 of t. Okay. So for system 1, the impulse response is h1 of t. For system 2, the impulse response is h2 of t, and these two are connected in parallel as shown in the diagram. Okay, this can be replaced, this parallel connection can be replaced by a single system with impulse response h1 of t plus h2 of t. So this parallel connection can be replaced with a single system whose impulse response is the combination of h1 of t plus h2 of t. So the combination of h1 of t plus h2 of t is a impulse response of the system. Now I can replace this parallel connection with a single system. For that system, the impulse response is the combination of h1 of t plus h2 of t. Okay, so simple. Two systems with impulse responses h1 of t and h2 of t are connected in parallel. We can replace those with a single system with an impulse response h1 of t plus h2 of t. So this is nothing but the diagrammatic representation of this distributive property, and this property can be used to break a complicated convolution into several simple ones. So this property can be used, this is used to break a complicated convolution, a bigger convolution into several simpler ones. So there is a complicated convolution, a large one. So I will make it into several simple ones, different parts, simple ones. Then the performing the convolution is very easy, and getting the output is also very easy. So the complicated convolution will be converted into several simple ones or simpler ones. Okay, so this is simply about the distributive property. Okay, simple. X of t star h1 of t plus h2 of t will be equal to x of t star h1 of t plus x of t star h2 of t. This is nothing but the distributive property. Okay, the complicated convolution is converted into several simpler ones. Simply here the parallel connection, the two systems with impulse responses h1 of t and h2 of t connected in parallel can be replaced with a single system with impulse response h1 of t plus h2 of t as shown in the diagram. So this is the diagrammatic representation of our distributive property. Okay, now with this I finished the distributive property. Now I am going on to the last one, the third one, that is associative property. So associative, we all know that associative property, A into B into C will be equal to A into B into C. That is the associative property. Now one of the important and useful property of convolution is associative property. One of the important and useful property, one of the very important and useful property of convolution is associative. That is, so with respect to convolutions, how can I write the associative property? X of t convolution h1 of t convolution h2 of t. X of t convolution h1 of t convolution h2 of t will be equal to x of t convolution h1 of t convolution h2 of t. See here, x of t is a separate one, that is convolution with the combination of h1 of t convolution h2 of t, that will be equal to x of t convolution h1 of t. This combination is convolution with h2 of t. See here, it is immaterial in which order the signals are convolved. So it is immaterial, so the order is not important here. So in which order we are convolving is not important, that is immaterial. So we can change the order. So here first I gone for x of t convolution, the combination of h1 of t convolution h2 of t. Here I gone for the x1 of t convolution h1 of t, that is making a combination, and I go for the convolution of h2 of t. Simple. So it is immaterial in which order the signals are convolved. So the order in which the signals are convolved is immaterial. It is not important. So first here I had taken these two as a combination, and x of t is convoluted with these two, and here I had taken x of t and h1 of t as a convolution, and I had convoluted this combination with the h2 of t. Hence it is immaterial in which order the signals are convolved. Okay, next, the series interconnection of two systems is equivalent to a single system. The series interconnection of two systems, series interconnection, the first one is serially connected to the second one, and they can be replaced with a single system, that is equivalent to a single system whose impulse response is the convolution of h1 of t and h2 of t. Okay, the series interconnection of two systems, let us consider as shown in the diagram. Given x of t is given as input to a system, let us consider system 1 whose impulse response is h1 of t, and the output of that one is given to another system, that is system 2 whose impulse response is h2 of t, and it is producing an output y of t. This combination is equivalent to another system with the impulse response as h1 of t convolution h2 of t. For that system the input is x of t, and it is producing the same output y of t, what that is produced for the previous system. Okay, so this output y of t is equivalent to the output that is generated by this system. So the associative property can be shown in the block diagram format as x of t is given as an input to a system 1 having an impulse response h1 of t, and the output of that system 1 is given as input to the system 2 whose impulse response is h2 of t, and it is producing an output y of t, and this output value will be equivalent to a system which is having input x of t, and the system is having an impulse response as h1 of t convolution h2 of t. The combination of h1 of t convolution h2 of t is taken as the impulse response of the system. Okay, so I am giving an input x of 2 to a system whose impulse response is a convolution of h1 of t and h2 of t, and that is producing an output y of t. Here the y of t, the output produced by this system is same as the output y of t produced by the combination of system 1 and system 2. Okay, so this is the diagrammatic representation of this associative property. Simple, x of t is given as input to system 1 h1 of t, and the output of that one is given to another system having impulse response h2 of t, and it is producing a y of t. This output is equal to a system which is producing as output y of t for a given input x of t, and having an impulse response which is equal to h1 of t convolution h2 of t. Okay, simple. The impulse response of the cascade of two LTI systems. The impulse response of the cascade of two LTI systems is the convolution of their individual impulse responses. The impulse response of the cascade of two LTI systems. See, this is an LTI system, this is an LTI system. Now these two are cascaded, that is the output of the first one is joined connected as input to the next one, then I can call that as a cascaded. Now see, the cascade of two LTI systems, these two are the cascade of two LTI systems. The impulse response of the cascade of two LTI systems is nothing but the convolution of their individual impulse responses, So here consider two systems which are cascaded to each other, and their impulse responses h1 of t and h2 of t. Now the total impulse response of the cascade of two LTI systems is the convolution of their individual impulse responses. Whenever two LTI systems are connected in cascading, okay, then the impulse response will be equal to the convolution of their individual impulse responses. Then the total impulse response is equal to the convolution of their individual responses, like this. Here the impulse response of these two cascaded LTI systems is equal to the convolution of the individual impulse responses. Okay, so this is the explanation about the associative property. Here in this associative property, simply the series interconnection of two systems is equivalent to a single system. The series interconnection of two systems is equivalent to a single system as shown in the diagram. So this is the block diagram representation of this associative property. This is one of the most important and useful property of convolution, and that can be represented as x of t convolution h1 of t star h2 of t will be equal to x of t convolution h1 of t star h2 of t. So this is how we will represent the associative property, and this is the block diagram representation. And finally, I can conclude that the impulse response of the cascade of two LTI systems is the convolution of their individual impulse responses. Simply, the series interconnection of two systems is equal to a single system, like this. So this is the complete explanation about associative property. So these are the properties, some basic and most important properties of linear time invariant systems. So these are the basic and most important properties of linear time invariant system, LTI systems. Important properties of LTI systems. Now I will go for the summary of today's class. What I explained in this class. First, summary. Let's go for summary. First, I explained you LTI system. First, I explained you LTI system. So, LTI, linear time invariant system. Okay, and then I explained you about LTV, linear time variant system. Linear time variant system, and then analysis of these systems. So these continuous time systems will be described by some differential equations, and that can be analyzed by using either Fourier transforms and Laplace transform. So which one is better? Here Laplace transform is easier and more convenient and more powerful than Fourier transform. I explained that one. Okay, so which one is better in Fourier transform and Laplace transform? After that, I went for the properties. Of this continuous time linear time invariant systems. I gone for the properties of this LTI systems. There I have three properties. First one is commutative property, next one is distributive property, and third one is associative property. I explain one by one. Okay, so this is a summary of today's class. With this, I am finishing today's class. Thank you, one and all.